Hello, this video is going to be a short discussion about the relationship between acidity and structure, and you can read this in your TRO text. Chapter 15, Section 10 has good reading there. So there are four main things we're going to talk about, two factors related to binary acids and two that are related to oxyacids. So binary acids are ones where you have hydrogen and one other element, and in these kind of acids you want to think about bond polarity. So an acid is something that generates hydrogen ions when you place it in solution. Therefore, the bond between hydrogen and the atom it's bonded to must be polar, with the hydrogen atom as the positive side of your pole. So if you look here at these three examples, the one on the left shows hydrogen bonded to lithium. It turns out that bond is a polar bond, but hydrogen ends up being the negative side of the pole. So that will not be an acidic molecule. If you look there in the middle, hydrocarbons, where you have a hydrogen bonded to a carbon, tend to not be noticeably acidic because that hydrogen-carbon bond is essentially nonpolar. Over there on the right, when you have your hydrogens bonded to a halogen, that is a polar bond, and it is polar with hydrogen being the positive pole, so that makes molecules such as HF acidic. So you need to have a polar bond with hydrogen as a positive pole. Other thing to consider is the bond strength. So strong acids have hydrogen ions that completely ionize. Therefore, stronger acids have weaker HA bonds. So in order for an acid to be strong, you want that H plus ion to break off readily. So the weaker the HA bond, the stronger the acid will be. And you can see this trend here at the bottom, and this gives us a hint as to why HF is actually a weak acid. So even though HF is a very polar molecule, giving a hydrogen with a very strong partial positive charge, HF has a relatively high bond energy, so it's a relatively strong bond, making it a weak acid, whereas hydrochloric acid has a weaker bond energy, so it's a smaller bond energy, a weaker bond, so it is a stronger acid. This visual I like from your book shows the relationship between, or the combined effect, I guess, of bond polarity and strength on the acidity of various molecules. So as you move across a row, you can see that the molecules would, or the bonds would become more polar, so you have a greater partial positive charge on the hydrogen, giving you a stronger acid. So HF is stronger than H2O, and HCl is stronger than H2S. So that's looking across a row. Going down a column, the bond strength will decrease as the atomic radius increases. Remember, as the bond strength weakens, the acid strength will increase. So HI is a stronger acid than HBr or HCl. The next two factors to consider have to do with oxyacids, and this is a very important group of acids that includes nitric acid, phosphoric acid, carbonic acid, all those polyatomic ions that we think of. So an oxyacid contains an H that's bonded to an O, which is then bonded to another atom, Y. And what's happening here is the electron density is being pulled towards the electronegative element Y, and this yellow arrow shows the direction in which the electrons are being pulled. And as electrons are being pulled that way towards Y, that makes the oxygen a little bit positive. That weakens the bond between O and H. That bond right there is being weakened as electrons are being pulled away from it, and that allows this hydrogen to break off more easily. And remember, stronger acids are ones that generate hydrogen ions more readily, so if it has a hydrogen breaking off easily, it's going to be a stronger acid. So the trend that we notice as the electronegativity of the element Y increases, the strength of the acid increases. So the more electronegative element you have, the stronger the pull on those electrons, the more you weaken that HO bond, and the more easily that hydrogen can break free. So if you look at this table at the bottom, you can see the relationship that as the electronegativity of the element Y increases, the K value increases. And remember, the K is products over reactants. So when you're talking about the Ka value, substances with a larger Ka value are generating more ions, and therefore they're generating more hydrogen ions, so they will be stronger acids. So higher Ka value, the stronger the acid is. The other trend to consider with these oxyacids is related and has to do with the number of oxygen atoms. So as the number of oxygen atoms bonded to the element Y increases, the acid strength will increase. And if you look at those examples on the bottom, we've got HClO4, HClO3, HClO2, and HClO. So the bottom one is hypochlorous acid. It is actually a weak acid. That top one is perchloric acid, and it is considered one of our strong acids. So you can say as you add oxygens, there's an increase in acid strength. One more kind of miscellaneous topic is thinking about the acidity of some oxides. These are actually ionic compounds versus the molecules we've just been talking about. But if you see a metal oxide like magnesium oxide, calcium oxide, if you were to take a solid metal oxide and place it in water, it would form a hydroxide, so it is going to be basic. It'll generate more hydroxide ions in solution. If you have non-metal oxides, so like carbon dioxide, any nitrogen oxide or sulfur oxide, these will generate acids when you place them in water. And some important implications of that, carbon dioxide combining with water creates carbonic acids. That's what's happening in our ocean right now, causing ocean acidification, lowering the pH. And you can see in this picture it shows nitrogen oxides, sulfur oxides combining with water to form either nitric acid or sulfuric acid. So that's what's happening when people talk about acid rain.